Hello everyone, I'm Rohit Uppala, a graduate student in Mechanical and Aerospace Engineering at Oklahoma State University. Today I'll be briefly talking about the topic, a machine learning approach to predict wind field data. This is a preliminary work in attempting to use machine learning for predicting wind field data. Spatio-temporal wind field prediction is essentially important for many fields like climate and weather forecasting, or wind field output estimation, or even for unmanned air systems. Our research mainly focused on small unmanned air systems and using these machine learning predictions for that application. It is very important for this because small unmanned air systems have low mass and are thus highly susceptible to wind effects. We also need some real-time predictions and pilot awareness in the events where these are used in complex terrains like urban environment. Numerical simulations for these cases are very computationally expensive since you would have to run a simulation for every flight test. So, why use machine learning? Neural networks have the ability to learn characteristics from extensive data available from simulations. This neural network, which has learned the characteristics from the data, could then be used for making predictions using some specialized networks like LSTM or RNN. The computational cost for this is substantially less expensive than running full-scale large eddy simulations or other computational fluid dynamics simulations. And even more, these ML models can be used for predictions in other setups without much changes necessary as compared to the large eddy simulations or other CFD simulations, where you might have to use a new grid or new solver setup, etc. Our main objective is to make an accurate prediction spatiotemporally for a three-dimensional wind field using neural networks. For this, we use the large eddy simulation data from Cloud Model 1 as the training dataset. But before training the neural network on this dataset, we use proper orthogonal decomposition to project the three-dimensional spatiotemporal data into a basis and consider only the important modes. An LSTM network is then chosen to make the time series predictions for these specific modes. Then these predictions are projected back from the model space to the 3D spatiotemporal field. And these are the machine learning spatiotemporal data. So the problem setup chosen for this is a stable boundary layer case. We take a domain dimensions of 400 meters in each direction with a grid resolution of 40 grid points also in each direction, thus making a grid spacing of 10 meters in all the three directions. The initialization is done with initial potential temperature profile consisting of a mixed layer with an overlying inversion, and the bottom surface is subjected to cooling. This is essential for the case of stable boundary layer, which is also known as the nocturnal boundary layer. Geostrophic wind conditions of 8 meters per second in the east to west directions are set up. Here it is the ux, or the velocity in the x component direction. And the Coriolis parameter is set to 1.39 into 10 power minus 4 second inverse. A fifth order Vino scheme with explicit time stepping and turbulent kinetic energy closure for large eddy simulations are used. The data is obtained for the training set after reaching a quasi-steady state of around 8 hours in this case. On the right, you can see an animation of how the stable boundary layer evolves till the 8 hours when it reaches the quasi-steady state. The test case setup consists of taking the three-dimensional data predictions from the neural network. So, for simplicity, we consider only the major component of velocity in the domain. In this case, the direction velocity in the x direction, or the u velocity component. Two major cases are investigated for these predictions. One is the short duration test case, where the model is trained from till 300 seconds and predicted for the next 60 seconds. We also have a split of training to prediction of around 5:1. Next, we take the long duration test case, where we have a training to prediction split of same 5:1, but now the model is trained for 3000 seconds and predicted for the next 600 seconds. For case 2, we take a different split of training and prediction data of 1:1. Hence, this is a much more challenging case than the previous one. So we train the data till 1800 seconds and then start predicting it for the next 1800 seconds. For accurate comparison, and consistency, all the results are shown in this specific format. The model coefficient evolution in time is shown for the first 8 modes, along with the comparison to the true modes for the respective case. Contour plots for the u velocity are shown in the xz direction in center of the domain, and a line plot is also made for the u velocity and compared with the LES data at the center of the domain in z direction. The locations of the results are also shown in this figure. Moving to the short duration test case results, we consider a relative importance index of 80%, which is determined by using the singular values obtained while doing the projection. This amounts to around 14 modes, and these are selected for training on the LSTM network. You can see the predictions on the bottom animation, where the blue line represents the prediction and the black the actual modes from the large eddy simulation data. We see that there is a good agreement between the model coefficient predictions and the actual values, with slight deviations in amplitude and phase. But as it turns out, for the u velocity prediction, there seems to be in close comparison to each other. On the left, you can see the contour plot between machine learning prediction and the LES result, showing with the contour lines. And on the right, you can see the u velocity line plot in the z direction in the center of the domain. They seem to be in good agreement as previously noted. For the long duration test case 1, we again consider 80% of relative importance index. Here it amounts to 40 of the modes, and these are selected for training the neural network. Again, we see that there is good agreement between the model coefficient predictions and the actual values, although there are slight deviations in the prediction and the actual case. The u velocity predictions are also very close to the LES result, as you can see in both in the contour plots on the left and also in the line plot in the right. However, now we move on to the long duration test case. Remember, recalling this test case where the training and the prediction split is made as 1:1. So it is trained for 1800 seconds and then the prediction is made for 1800 seconds. 80% of relative importance index is considered. So again, 40 modes are selected based on this criteria. However, for this case, the model coefficient predictions are not in good agreement, but are still comparable. We can see that especially for modes 1 and 2, there seems to be a phase difference between the predictions and the actual data. And for the mode 3, you can see there seems to be a large offset both in the training phase and also in the prediction phase. We feel that further analysis is required in determining how close the prediction is with the LES data. If you look at the contours for the machine learning prediction on the left, and for the line and the u velocity line plot in the z direction on the right, we see that there is some close agreement. But however, as we recall, we need further analysis on comparing other flow statistics before making a solid conclusion. In conclusion, machine learning predictions are consistent with the actual values both for the short and long duration datasets. As expected, for the large dataset, they seem to give better predictions for model coefficients and thus the u velocity components. However, for the split of 1:1 between training and prediction, there is some deviation from actual values and more work needs to be done in better training the network. For future work, we are looking at using data assimilation, which could be used for correcting the predictions over long durations, and convolutional neural networks with encoder-decoder type setups coupled with LSTM network that could be used for complex flow structures with obstacles like buildings. We would like to acknowledge the support of National Science Foundation. Our research work is covered under their grant, and also the High Performance Computing Center at Oklahoma State University. We would also like to acknowledge Cheyenne, the High Performance Computing support at NCAR's Computational and Information Systems Laboratory. Thank you.